Welcome to statistics. So we're going to look at standard normal. Okay, this is a distribution, and as a general rule, when we talk about data, we normally can kind of fit our data into a particular category, and that's one of the goals that we're trying to get after is figuring out what shape, and I use that term kind of in quotes, but not entirely, what shape our data is. And when we go and we graph our data according to frequency, and it gives us, say, a normal distribution, which is your standard bell curve, which is what I have in front of you. And I'm going to talk a little bit about the different points and pieces and aspects of this in a little bit more detail. And I have another video that just is entirely about about normal curve, but here the focus is going to be the standard normal curve and the differences between this and the normal curve. When we talk about the normal curve, the idea is that we are referring to this idea that we're breaking up all of our data. It has this basic shape if we create a histogram and plot it according to frequency, and we get this basic shape of our curve. And one of the big ideas is that from here to here is roughly, and I do say roughly, 68%. It's approximate. It's actually 34.1 and 34.1, so this is approximately 68.2 if you want to be more precise. If you extend this out to include this section right here, you're getting up to the point where you're at about 95% of the data, and then you move out a little bit further. You include to here and to here, and now you're up to 99% of the data, and you keep going. And this is based upon taking your average, which is mu here, and adding or subtracting standard deviations, which is what that little swirly piece is. So our standard deviation, we're using this symbol right here, which is lowercase sigma. And then for our mean, we're using mu. Now, a couple pieces that we need to point out here is most of the time, these two pieces are approximations, right? So a lot of times what we're going to use instead of sigma and mu is we're going to use S and X bar, because these are based upon observation. Okay, or another way to say that they're based upon observation, they're based upon data that we've collected. Okay, now these values over here are what we call our ideal. Okay, and they are based upon what it would be for the entire population if we could collect all that data, but normally we can't do that. So we don't, these values, these symbols at least, are for the most part kind of interchangeable. And I say that loosely, but we can kind of use them back and forth. When we say mu, we're talking about mean. When we use X bar, we're talking about mean. It's the matter of the details associated with using one or the other. So if we want to talk just about the ideal mean, we'd say mu. If we talk about an actual value that we know, an observed mean based upon the data set, we'd use X bar. I'm not going to be terribly picky. You use one in place of the other, but keeping track of those when we use some formulas will be very important. So just keep track, just pay attention to those as we go through that. Now, this is all based upon the normal curve, is what I have down here. When we go to standard normal, another piece that we use a lot of times for this, you'll see this written as a z-score, okay? Or a z-value or z-standard. There are lots of ways it's said. Two basic aspects of this that are extremely useful to using a z-score. Let me write that a little bit cleaner. Namely, that when we talk about standard normal, we're saying that the average is 0, and we're saying the standard deviation is 1. Okay? Now, what that does for us is it kind of simplifies all these pieces that we're talking about here along the bottom. So now we're talking about, instead of the mu here being a particular number of some sort, it's just 0. This is 1, this is 2, this is 3, this is -1, this is -2, this is -3. So instead of talking about this first location right here being mu or X bar plus 1 standard deviation, we're now talking about this being a z-score, this being a z-value of 1, this being a z-value of 2, this being a z-value of 3. So we can even talk about in between, like a z of 1.5 means we're in between, somewhere in between one standard deviation and 2 standard deviations away, which if we say 1.5, it'd put it right about there, which allows us to be able to have all sorts of other conversations. Now, why this is useful, or why do we care about this? Well, namely, it has to do with how we want to use the data. Sometimes this isn't what we want to do. This isn't necessarily the most useful way to do this. And the idea behind standard normal is that we're standardizing everything so that the average is 0, right? So that mu value or that x bar value is 0. So let's just take a couple of pieces of examples here real quick. Let's say that we have this normal curve, it looks something like this, and let's say that the mu value, or rather the x bar value, is 885, right? And here is 1 standard deviation away, and here we're saying the standard deviation is, I don't know, 35.1, okay? So this would be scenario 1. Scenario 2, we have another normal curve. Our data is normal. In this instance, we have x is equal to 870. And then we have, of course, 1 standard deviation over. And here we're saying, let's put some values here. Let's say this with set 1, this would be with set 2 over here. This would be standard deviation with set 1. We'll call this standard deviation with set 2. And standard deviation with set 2 is 33.7, okay? Now, if these are our 2 data sets, what does this really mean, right? How can we compare this? So let's just say that we're talking about these are pass rates on a particular exam, some type of standardized exam of some sort. And we're looking at 2 groups of people, or we're looking at slightly different, we're looking at the same grouping of people. Let's just say males and males on an exam. So this is males on a, let's just say a reading test of some sort, okay, in Indiana, okay? And this is males on a reading test in Texas, okay? So are they the same reading test? Maybe, maybe not. But how do we compare them if they're not the same test? If they're the same test, we can obviously make a very good inkling here, or a very good statement about how the average is lower on one and the standard deviation is larger on the other one. So here in Indiana, we'd have a higher average score for those male students, and the spread between the students is larger. So there's a greater variation between what students would be able to do on the exam. In Texas, the score is lower, the average score is lower, and the spread is a little bit smaller. Which one has the smaller spread, though? I mean, which we can't really, it's very difficult to compare these if these are reading test 1 and this is reading test 2. Are these really comparable? Which one really did better on the exam? Well, what if the test for this top exam here, what if the test ranges, the possible scores were from 700 to 900, and down here the scores were from 650 to 850. Well, which one did better? And that's where we start getting into these questions about this. And this is where standard normal is extremely effective, because what we can then do if we standardize this is, instead of talking about having 2 different averages, is we go through this process where we take this average and we make them essentially the same. We make them both a z-value of 0. So we'd say this mu value here would be 0, this mu value right here would be 0 as well. And then when we start talking about 1 standard deviation away, it has been standardized to being of the same caliber. And then we can actually see which one has the larger spread and which one has which one is actually doing better, if you want to be able to read into that, because then we can really start to analyze this a little better. And this is the strength of the standard normal curve, is it allows us to center everything around the same place and say, well, we have 68% of the data in here, so we'd still be having that. There'd still be 68% of the data here. and we'd still have 68% of the data there, even after we standardize it. And then now we know we're talking about 68% of the data here, 68% of the data here. How many or what do these scores look like that contain 68% of the data? Okay, and that's where we can start to deal with this a little bit better, because now we know what 68% entails, and then also we know what standard deviation entails, so we can start to get a better idea of how these two groups on these two different exams are comparing against each other. Okay, so next thing we need to do is figure out how do we actually go through and standardize that data, and that's going to be the topic of a whole nother video. So I hope you enjoyed this. I hope this was useful. Please reach out with questions, comments as you have them, and I'll be happy and do my best to answer them in the best possible speed. Take care.